Right now, we're approaching the limits of how small we can make classical computers. If you make transistors, the switches inside computers, any smaller, electrons will be able to quantum tunnel through them. But can we use these problematic quantum effects for good? Quantum computing uses quantum phenomenon for a new avenue of computing. What is quantum computing, and how is it different than regular classical computing? The difference between classical and quantum computing arises from the fundamental physics that they use. Classical computing uses classical mechanics, while quantum computing uses quantum mechanics. Classical mechanics is deterministic. We can predict the behavior of objects with certainty. However, when we zoom into the realm of particles, we can only work with probabilities of states. At this scale, particles are best described as waves. For example, an electron is best described as the excitation of the electron field. Physicists found that when shooting electrons, one by one, through two slits, the electrons produced a wave interference pattern, an effect traditionally seen from waves. This pattern indicated that they had wave-like properties. Similarly, other properties of particles are wave-like in nature. They're not definite. When a particle interacts with another particle, the properties of the particle, instead of maintaining their wave-like nature, choose a state. In this case, a photon interacts with an electron, making the electron choose to be spin up. Before the interaction, the property of spin is in a superposition, in which the spin is up and down at the same time. Superposition is strange to us classical beings, but we can exploit this property for quantum computers. Quantum computers are engineered to prevent interactions from the outside, while still letting particles on the inside to interact with each other in a superposition. This can prove difficult, because even the resistance to a metal can disturb the superposition. Physicists have to jump over technical hurdles such as cooling to achieve superconducting in order to preserve the superposition. A classical bit can only be 0 or 1, while a quantum bit can be a superposition of both. To express this superposition, physicists use bracket notation and linear algebra. For example, it's 50-50 whether a coin spinning in the air is heads up or heads down. The state of being heads or tails is expressed in these brackets, and the square roots of the probabilities are the coefficients. 1 over root 2 squared is 1/2, meaning a probability of 50%. On the quantum scale, whether an electron is spin up or spin down can be expressed the same way, and more abstractly, whether a qubit is 1 or 0 can be defined by the same notation. These numbers might look familiar if you're taking trig. The probabilities from bracket notation are meant to be defined on what's called a Bloch sphere. Another handy way of representing these probabilities is through vectors from linear algebra. The top number represents the probability of a state 0, and the bottom number represents the probability of a state 1. This concept will be important later. Back to classical computing, we can expand on bits further and create gates. These gates transform bits using circuitry based on transistors, tiny electrical switches. The NOT gate takes an input and inverses it. A 1 becomes a 0 and a 0 becomes a 1. Quantum computing has a similar gate called the poly-X gate. Here's where linear algebra comes in. Quantum gates can be represented as matrices since they're linear operators. This fact also makes them reversible. Multiplying the vector of the qubit by the matrix of the gate is the same as applying the gate to the qubit. In the poly-X gate, the probabilities of the states are switched. There are also more complicated classical gates, such as the AND gate. Another important quantum gate, the Hadamard gate, creates a uniform probability, at 50-50. In this case, a qubit is converted from a state of 0 to a 50-50 superposition of 1 and 0. I simulated this circuit in IBM's quantum computer. When the computer measures the particle, it's either a 1 or a 0, but when we look at the average result of the system after a computer runs the program several hundred times, we find that the probability of a 1 or a 0 averages out to a 50-50. Here's the Bloch sphere visualization. I also created a circuit with 2 qubits and Hadamard gates. You can pause the video if you want to check out the results. By combining gates, you can create a more complex machine. In classical computing, you can create a Turing machine with a server memory and a couple of gates. Here's one adding 2 plus 7. As it encounters any gaps, areas where a clear bit is surrounded by 1s, it will fill in the bit as a 1, adding 1. The machine continues until it finds a clear bit that has another clear bit to the right of it. Finally, the machine removes a bit at the end, subtracting one, to cancel out the one that was added to bridge the gap. Although this machine may seem very simple, the fact that it can perform a result with some simple rules makes it powerful. By expressing the rules as inputs in binary, you can create any program that can perform a task given the rules, a programmable computer. All computers are based on this abstract idea of a Turing machine. Likewise, physicists can program a quantum computer to execute quantum circuits. With some clever math, these circuits can produce some remarkable results. Factoring is a difficult problem for most classical computers. You use it for cryptography, which secures your bank account, phone, and cryptocurrencies. Cryptography uses a large prime, called a key, to scramble your message. The only way to unscramble the message is to have the inverse key. Even though a hacker can find the inverse key, they would have to cycle through a lot of possible keys, making the process lengthy. Regular classical computers would have to go through many primes to unscramble the message. However, quantum computers can do the same task very efficiently by running parallel computations. Here we have the runtimes of the current best quantum and classical algorithms for factoring. The classical algorithm, the general number field sieve, has the exponential runtime, meaning that for large numbers, the runtime becomes incredibly large. On the other hand, Shor's algorithm has a polynomial runtime, meaning the runtime does not become quite as large for large numbers. This is because, unlike a classical computer, a quantum computer can run the algorithm in parallel by evaluating many guesses at a time using superposition. But wait, how can quantum computers run an algorithm in parallel? When measuring the result, it collapses down to only one state. It's like finding all the information of all the pixels in an image, and then when you try to display it, only one pixel comes through. The superposition collapses down to one state. Instead of observing the result directly, the algorithm encodes the true answer in the probabilities of the states. With some clever math, the probabilities are arranged as a cosine wave, and the true answer is encoded in the frequency of the wave. Another circuit called the quantum Fourier transform can take this wave and convert it into the frequency, and then from there we can get the true answer. These incredible computations are only the tip of the iceberg. Feynman and Benioff created the idea of the quantum computer to simulate quantum physics. Simulating quantum physics might sound boring. The real world uses classical mechanics. Or does it? The small-scale implications of quantum mechanics affect the classical world. For example, electron clouds, quantum in nature, determine the bonds in a molecule. Furthermore, they affect the reactivity of the compounds, governing how certain medications can affect the body. In 2013, the Chemistry Nobel Prize went to 3 people who used quantum computing to give us a better understanding of the reactivity of compounds. Simulating quantum mechanics and factoring are only a few of the problems that computer scientists believe that quantum computers can compute much faster than regular computers. These tremendous advancements in computing are a result of the fundamental physics that quantum computers use, and hopefully further research will adventure this new computing approach.